Well, anyway, we need to know the properties of these operations just to uh, uh, do some symbolic calculations. Often we have to do symbolic calculation to understand, to prove something, to see the reason of some phenomena. Okay, so a theorem in this slide is listing the properties of operations. So let A, B, and C, they are the B matrices, and A, B, C be scalars, numbers, real numbers. And assume that the sizes of these matrices are good. The following operations can be performed. For example, A plus B, so first property, commutativity or commutative property of addition. A plus B is B plus A. Okay. One, we say sizes are good. For first property, just this means that sizes, A matrices A and B, they have the same size. They have the same size. You know that. Then A plus B is defined, B plus A defined, and this theorem is saying that they are indeed equal. Easy, because of commutativity of addition for numbers. Associative property for addition. Okay, that's also true. Zero. Assume that O denotes some zero matrix of the same size as matrix A. Then A plus O plus A is A. I said that zero matrices, they play the role of zero for numbers. Okay, and distributive property of multiplication by scalar. Okay, so here also some misprint, something is missed here. Okay, for a property for distributivity of scalar multiplication with respect to addition should be a complete statement of this property. This is similar. This is also this is important. The property 6 does have special name, this property, but this is important because of indeed we consider matrices some objects of some kind, and numbers, they are another objects of another kind. So this property 6 shows that as the multiplying matrix by number, it's okay. You can use this as for numbers. So multiply C by B, then B by A. You can just multiply C by AB and get the same result. And okay. So surprising property of matrix product is it is associative. Okay. So if the products BC, AB, and ABC, AB by C, they are defined, then we have this equality shown in first property shown in this theorem. Okay, distributivity of addition with respect to multiplication with respect to addition. Also we should distinguish left distributive property, right distributive property. Okay, why we are giving 2 and 3 because of you'll see again identity. This is as number 1. It is neutral with respect to matrix multiplication. Okay, and this is easy. Why we, for example, give 2 and 3 because of multiplication is not commutative in general. So that's why we distinguish. Yeah, we give separately property 2 and property 3. Distributivity property of multiplication. And yeah, many properties can be proved easily. For example, commutativity is easy. I said this consequence of commutativity of addition for numbers, and yeah, do you see? It's true. Because what is entry ij of matrix A plus B? This is Aij plus Bij. What is ij entry of matrix B plus A? This is almost the same, just first Bij, then plus Aij. But as numbers, they are equal. So it follows these two sums of matrices, they are equal. A plus B is equal to B plus A. And some example showing, yeah, you can add the first A plus B, then plus C, or another way is just define first, calculate B plus C, then plus A, and you would have the same result. So this is, I think, about the associativity of addition. And a few words about the complexity of operations. Mainly, complexity problem appears with respect to matrix multiplication. So let's consider this situation separately. So assume that we have some product AB of matrices. So assume that size of A is M times R, and size of B is R times N. Okay. Then if you remember the calculation of product, then you see we have to calculate Mn times dot products, and each dot product contains R multiplication of numbers, R multiplication. So we, from the complexity theory view, from the view of point complexity theory, addition is easy. So we don't care about addition. We just count how many multiplication, which is multiplication. It is much complex operation, much difficult operation from the point of view complexity theory. So how many multiplication involved in computation of product AB? M, R, N. Okay, if sizes are as above, M times R and R times N. So sometimes you can use this fact to, so assume that we are going to calculate the product of three matrices ABC. So from this surprising property of associativity of multiplication. So you can do the following: first calculate AB, then multiply the result by C, or you calculate first BC, then multiply the result from the left side by A. And previous theorem, you get the same result. But now let's think about the complexity. Which way is better, easier? So we just count how many multiplication involved in each case. And this is sometimes important. Let's see example 10. Okay. So we are given three matrices ABC, product ABC, yeah, is defined, it exists. Now we have two ways. First, when we calculate AB, then multiply result by C from right side. Let's see how many multiplication we use. For AB we use 12, yeah, I think. Okay, so 12, and for the last we use another 6, so 18 multiplication. And second way is calculate first BC, then multiply the result from left by A. Let's calculate how many multiplication involved in this case. So BC involves 6 multiplications, yeah, 3 and 3, 3 plus 3. And if you multiply BC by A from left, you use another 4 multiplications. Okay, so in total you have, in the second way, 10 multiplications. Yeah. So yeah, I said already that yeah, I just counted the number of multiplication involved in first way. Yeah, for AB we need 12 multiplications, and for AB multiplied by C another 6 multiplication. In total we need 18 multiplications. Second way uses only 10 multiplications. BC involves 6, and when you multiply BC by A, for another 4 multiplication involved. So in total you have 10 multiplication. So you see, second way is better. So this is just some view of point from complexity theory. Yeah, it is always presented in the linear algebra. If you look at your textbook, almost each chapter of textbook contains some comment about the complexity of methods you are using for solving problem presented in that chapter. Okay. Please read them and try to understand the meaning of these comments. Okay, they are important when you do some real work involving methods of linear algebra. Okay, always you should know which. Yeah, if you have several ways to do some work, yeah, you should know. Intuitively calculate which one is better from complexity theory, from the viewpoint complexity theory. Okay. Yeah, so second way is better, obviously, because almost 2 times better than the first one. Yeah, so you use to calculate numbers, apply some rules. So the famous rule is the following for numbers. If you have equality, AB is equal to AC and A is non-zero number, then you can cancel. Yeah. So, and get that B is equal to C. But this rule doesn't work for matrices. So this is caution about this mistake, common when you do some exams, quizzes, and during your study of linear algebra. Please. So take care about this problem. This is not true for matrices. And also another rule or method is saying the following: if product is 0, then some factor of this product is 0. In particular, if PQ are 0, then P is 0 or Q is 0. Okay, and for matrices, this rule is also not true. Okay, so about last property. Yeah, you can find two matrices, P and Q. Their product is 0 matrix, but none of them, P nor Q, they are not 0 matrices. Okay, none of them 0 matrix. And also you could find matrices A, B, C satisfying the equation AB is equal to AC, and A is not 0, but nevertheless B and C, they are different. Okay. Look here, an example. Example 11. So as the first property, yeah, so a caution about first property, yeah, which is true for numbers but not true for matrices. So look at the matrices A, B, and C. A is not obviously non-zero, and you can check that AB is equal to AC. If you apply the rules, matrix multiplication, calculate matrix multiplication, you see that they are both equal to the matrix 3, 4, 6, 8. But B and C, they are not equal. Yeah, remember the first notion of first relation on matrices, when matrices are equal. B and C are not equal. And why another rule is not true for matrices. Consider matrices P and Q. P is 1 minus 2 minus 2, 4. Q is 2 minus 6, 1 minus 3. And then multiply them. You'll see that product is a 0 matrix. But none of P and Q is 0 matrix. Okay, so please, this is just caution for you. Some rules that true for numbers may be not true for matrices. Please remember this. And okay, now, yeah, among the matrices, square matrices are important. Why? Because if you have two square matrices of the same size, you can add them and get again matrix of the same size. You can multiply them, again get the matrix of that size. Okay, so square matrices of fixed size, they form some structure where we have completely defined two operations, addition and multiplication, also of K. If you multiply square matrix by any scalar, then you get again square matrix of the same size. That's also, it is closed under multiplication by scalar. And another notion that can be defined for square matrices, their powers can be defined. So what is A power K? Just multiply A by itself K times. A to K is A multiplied by A and so on, A K times. So A to 1 is, A0 is this identity. By definition, please look at this theorem, last point of the theorem. A to the power 0, this is identity. N, where N is exactly the size of a square matrix, N by N matrix. And A power 1 is a itself, and then you can define a square, a cube, inductively. Okay. So powers can be defined, and they satisfy the properties mentioned in theorem here. A to r multiplied by a to s is a to r plus s. This is an easy consequence of the definition. A to r to power s is a to rs, also direct corollary of definition. Okay. Another example, again from the view of complexity, how to quickly compute the a power 4. Easy. Two squaring. First squaring, a square is, you see, initial matrix is n minus 2 minus 1, 0. Its square is 3 minus 2 minus 1, 2. Square it again, and you get a to 4. So, and the wrong way is to get a to 4 by the following. So you get a square using one matrix multiplication, then multiply a2 by a and get a cubed, and multiply again a and you get a4. So this is not the best way. Okay. Best way is just squaring. And also there is notion in complexity theory that the best way of computation of powers of matrices or any other objects, this is by square and multiply method. This will be explained later on in some courses on related to complexity theory, I hope. So here you see, easiest way is squaring and again squaring. And some example related to symbolic computation. So assume that A and B, they are, for simplicity, they are square matrices of the same size, and you have this expression related to these matrices. And as in example 13, okay, you ask to simplify this expression using properties of matrix operations. Okay, so you expand first product. It is what is it? A square plus 2ab, and expand next product 3b by expression in parentheses 2a minus b. This is 6ba 3 minus 3b square, and then count the numbers of a square. They cancel because you have one a square and minus a square, and 7b square minus 3b square, we have 3b square. Okay, and let's count ab and ba. How many ab we have? 2 minus 5ab minus 3ab and plus 6ba. Okay, that's all. You should stop here. And some students do mistake in this moment, using the wrong commutativity property. It's not true for matrices. So it's not 4b square plus 3ab. No, you should stop here, because ab, ba, they are not equal in general. Okay, so that's another caution for you when you do some symbolic calculations related to matrices. Well, so first lecture it was about systems of linear equations, And you see here, these systems can be expressed as matrix equation. Look here. So first, you see the system is given by its abstract variables x1, x2, and so on, xn, abstract coefficients aij, and abstract constant terms b1, b2, and so on, bm. Okay, and now, if you collect coefficients of these equations, then you get some matrices of the size m times n. Okay, if you write the variables of this system in a column, you get a column of variables denoted by capital X. Okay, and it consists of x1, I'm reading from top to bottom, x2, and so xn. And look, could we multiply a by x? Yes, we could, because a length of a is n and height of x is also n. So product ax is defined. And what is a result? Because size of matrix A is m times n, and size of matrix X is n times 1, the resulting matrix size is m times 1. This is column, but of the height m. And if you now calculate entries of the product mass, you'll see this is exactly the left-hand sides of the equations in this system. So this system can be written shortly using matrix notation. You see in the last row this, AX is equal to B, where matrix B is again column of height m. Okay. Also, I'd like to say some comments about the number of solutions of a system of linear equations. It may be inconsistent, and number of solutions 0 may have unique solution. Number of solution is 1. And last case, if you remember the Gaussian elimination method, reducing the augmented matrix of the system to the REF. Okay, if in REF, after deleting last row of constant term, you get identity matrix. This is unique solution. Okay, if not, then there are free variables. Okay, if you remember the lecture 1. This means that then, because of this presence of free variable or variables, there may be many free variables, the number of solutions will be infinitely many. You know why? Because when we write the solution, these free variables assumed to be equal some parameters, and these parameters S, T, R, they may take any real value. So you have infinitely many solutions. Okay, this is just comment about the numbers of solutions of systems of linear equations. Some special matrices, I don't know if they will be used by teachers of the practice classes, but nevertheless, let's mention them. Okay, so square matrix is called to be idempotent if A square is A. You see example here. Okay, example 14, you see some idempotent matrix. A square is A. Square matrix is said nilpotent if for some positive integer its pth power is 0 matrix. Yeah, here should be no number zero matrix. Okay. This, sorry, I like to. Yeah. Here should be not number. Here should be O. Yeah. It's not number. Okay. Sorry. Yeah, it can be easily. For example, B is nilpotent matrix from example 14, second example. And this a list integer P for which this Pth degree is 0 is called degree of nilpotency of this matrix. Okay. This is just, okay. Yeah, you can, I hope that you can skip it because I think that this question will be out of syllabus maybe.